So hello friends, today again we have just gathered here to complete the remaining part in the mechanical properties and their testing. So today we will just go with the stress strain diagrams. So in the last lecture we have just covered up the tensile test, and basically whatever the stress strain diagrams are there, which is the very important part related to the tensile test. So what is the meaning of stress and what is the meaning of strain? Already this particular part you have covered in the engineering mechanics. So basically the stress, it is related to the load applied on the surface area, but whatever may be the changes are occurred which is inside. So the example is, suppose the mental stress. When we are talking about the mental stress, so that particular stress we cannot be able to visualize. So similarly whatever may be the changes are occurred, so the basic difference between pressure and stress is that pressure that externally we are applying on the surface, and stress which is internally generated inside the component. So you may say that it is just one kind of that opposite reaction when we are applying the forces on the body externally. So when we are applying the forces on the body externally, the inside the material, some sort of that stresses has been generated which is related to that particular force to the area. Now what is the meaning of strain? So strain is nothing but it is just a ratio of change in a dimensions to the original dimensions. So that changes might be the length, or might be a breadth, or might be a diameter, anything. So whatever may be the change, according to that change, the change in a dimensions to the original dimension, that ratio is particularly called as a strain. So the units for the stress is Newton, that is, it is related to the load upon area. So area we are generally measuring in meter square. So it will be a Newton per meter square. Strain, that is change in a dimension to the original dimension. So that's why it is the unitless quantity. So basically the stress strain diagram, it is a tool for understanding the behavior of the material under the load. So stress strain diagram helps an engineer to select the right material for specific loading conditions. So when some sort of that certain kind of that loadings are there, so for the specific loading condition to choose a particular material, that stress strain diagram plays a very important role. So it is the graph that represent how a part behaves under the increasing load and used by the engineers when selecting the material for the specific design. So when you are going for the selection of material, that stress strain graph plays a very important role. So what is the stress strain diagram? So basically there are three regions are there in the stress strain diagram. So first is the elastic region. So this portion is generally represented as a linear relationship between stress and strain. If the load is released, the specimen will return to its original dimension. So in the elastic region, when we are removing the load, again its original size and shape we can be able to gain. So second phase is plastic region. So in this particular portion, the specimen being to yield the maximum strength of the specimen occurs in this particular zone. The specimen endures some permanent deformation that remains after the load is released. So already we have seen about the plastic deformation. So the plastic region is that when even we are removing the load from that particular material, that material will not be gain its original size and shape. So that deformation is permanent, which is called as a plastic region. And the third region is the rupture, that is the failure or fracture, we can say, the point at which the specimen breaks into two parts. So that is the failure. So these are the three regions in the stress strain diagram. So first is the elastic, second one is the plastic, and third one is the rupture. So this is the stress strain curve for the ductile material. So here that specimen has been shown. So first zone is the elastic limit. Second is the yield point where the plastic redeformation has been occurred. Then that strain, so here that stress will be constant but strain will be increasing. That is the deformation will be starts, and the ultimate tensile strength, that is the maximum stress that material can be able to sustain, and finally after the neck formation the rupture, that is the fracture, may be occurred. So this zone is called as an elastic region, where even we will remove the load from the material, that material will be gain its original size and shape. So this is the elastic region. After the elastic region there will be a yield point. So in this particular zone, that is whole zone is known as for the plastic region. In this case material cannot be able to regain its original size and shape, and finally the material will be breaks. So what is the stress strain diagram? So the stress strain diagram are generated experimentally through the performance of controlled tensile test using the fabricated test specimen. So the applied load and displacement are monitored during the test and are used to calculate the stress and strain respectively. So this is the component where we can be able to see this will be the neck formation, and after that that rupture will be occurred. So to calculate the stress and strain, the applied load and displacement has been monitored. So this is the UTM machine which we have seen in the last lecture, just used to conduct the tensile test. So the stress strain diagram. So basically the stress strain diagram differ in form of various materials. So material to material that stress strain diagram will be different. So the engineering materials basically classified into the two phases, that is the ductile and brittle material. Now what is the meaning of ductile material? A ductile material is one having relatively large tensile strain up to the point of rupture, like structural steel and aluminium. So basically the steel and aluminium are known as an ductile material, whereas the cast iron and concrete, which is having the very small strain, means there is no any deformation occurs, so it is the brittle material. Now just to understand what is the meaning of ductility and brittleness. So ductility, it is the ability of material to deform under the tensile load. That is nothing but the high percentage of elongation and percentage of reduction of the area, that is indicated ductility. If the percentage of elongation is very high, that is the ductile material. And brittleness, that is the material failure with a little deformation, means no any much deformation is occurred but the material will be failed. That is nothing but the low percentage of elongation and low percentage of reduction of area, that indicates the brittleness in the material. So the fundamental of fracture. What is the meaning of fracture? Simple fracture is the separation of a body into two or more pieces in a response to an imposed stress that is static. So here you can be able to see some sort of that forces. So for the tensile test, the forces are applied on the component along the center, and these are the two equal and opposite forces. For the compression, there are the forces towards each other and applied along the center, and this is the shear stress. So this is the diagram, stress strain diagram for ductile and brittle material. This is the general schematic diagram for ductile material and brittle material, how it behaves for the brittle material and ductile material. In the next part we will see this thing detailedly. Now in case of stress strain diagram, these are the phases which is very important in the stress strain diagram. So the first phase is known as the proportional limit, that is nothing but it obeys the Hooke's law. So what is that Hooke's law? Hooke's law generally indicates with the stress is directly proportional to strain. within the proportional limit. So this is the Hooke's law. So when the stress is directly proportional to the strain, it known as an Hooke's law, and the first phase of stress strain diagram is the proportional limit. So here we can be able to see that proportional limit. So up to this particular phase here, it will be indicates the proportional limit. So in this case, the stress is directly proportional to the strain. Here we can be able to see the stress is increases along with the strain. So it will be a directly proportional. So from the origin point to the P, it is called as a proportional limit. The stress strain curve is the straight line. Here we can be able to see. So Hooke's law, it is nothing but the in the proportional limit, the stress is directly proportional to the strain. The constant of proportionality is called as a modulus of elasticity or Young's modulus and is equal to the slope of the stress strain diagram from O to P. Then the stress is equal to modulus of elasticity into strain, or we can say that the modulus of elasticity E is nothing but the stress to the strain. So here when this strain will be comes into this direction or in this particular zone, so it will be a in the divided factor. So modulus of elasticity E is equal to stress to the strain. So the next is the modulus of elasticity. So to describe the elastic properties of linear object like wires, rods, which are stressed or compressed, a convenient parameter is the ratio of the stress to the strain. It is called as a Young's modulus or modulus of elasticity. So Young's modulus can be used to predict the elongation or compression of an object as long as the stress is less than the yield strength of the material. So in many material, the relation between applied stress and resulting strain is directly proportional, and the graph representing those two quantities is the straight line. So here these are the different phases of stress strain diagram. Here we can be able to see this is the proportional limit. Then this particular zone is known as an elastic limit. So in the elastic limit, where we can be able to gain the original size and shape even after the removal of the load, but after the elastic limit, the first phase is occurred, that is the yield point, where the plastic deformation has been started. So from this region, we cannot be able to gain the original size and shape of that particular material even when we are removing the load. So after that, the deformation started and it will be reached to its maximum point, that is the maximum stress it can be able to occur, and this particular point is known as the ultimate strain, where we are getting the maximum stress, and after that zone the neck formation has been started and the material will be gets fractured. So that is, it will be breaks into the two pieces. So this is the rupture strain. So these are the general values. It is just for the reference purpose. What is the modulus of elasticity of the different material? It is given. So the stress strain diagram. First, we have discussed about the elastic limit, then yield point. So what is the yield point? So yield point is the point at which the material will have an appreciable elongation, or we can say the slight increase in a strain above the elastic limit will result in a permanent deformation. So the exact permanent deformation will be started at the yield point, and this behavior is called as the yielding for the ductile material. So the less ductile material such as aluminium and the medium to high carbon steel do not have a well defined yield point. So basically for the aluminium or any medium to high carbon steel, the yield point has not been there or it is not specifically defined. So the upper yield point, which corresponds to the load reached just before the yield start, and the lower yield point, which corresponds to the load required maintaining the yield. So these are the 2 points in the yield phase, that is the upper yield point and the lower yield point. So to determine the yield strength of the material, that lower yield point has been used. So this will be gets cleared again. Here this is the elastic region, which is shown with the dark blue color over here. Then this is the yielding point. So this will be the proportionality limit, that is the sigma PL. means stress of the proportional limit. It is known as a sigma PL. Then yield stress, that is the sigma Y, which is indicated over here. So it has been just started the plastic deformation. Then next, that is the ultimate stress, or before that ultimate stress. Here we can be able to say that the strain hardening has been started over here. This is the elastic behavior and this will be the plastic behavior. Then the very important part, that is the fracture stress. So here in this particular point, here we can be able to see the plastic deformation. So yield stress, then the elastic limit, then the proportional limit. So all those limits has been shown over here. So this is the generally the stress strain diagram for the mild steel. So in this particular stress strain diagram, here we can be able to see that this is the elastic uniform plastic elongation and the necking portion. So this will be a proportional limit. E, it is the point where the elastic zone it is there. YU means yield, upper yield point, and this will be the YL is nothing but the lower yield point. Then this will be the S, that is the UTS, or we can say the ultimate tensile strain, and B is the point where exact fracture has been occurred. So these are the some sort of that snaps for the specimen behavior. Here we can be able to see the specimen behavior. So uniform elastic deformation. Here we can be able to say that after removing of the load, that material will be gain its original size and shape. But in this particular portion, the plastic deformation will be started. So the component will be permanently losing its size and shape, and it cannot be able to regain. So this will be the neck formation in this portion. Here we can be able to observe, and at the last phase the fracture will be occurred. So that particular component has been breaked into the two pieces. Here we can be able to see. So basically the yielding or yield strain, what is the meaning of that? This is the upper yield point and this is the lower yield point. So the most structure are designed to ensure that only elastic deformation will result when a stress is applied. A structure or a component that has the plastically deformed or experienced a permanent change in a shape may not be capable of functioning. Okay, so these are the representation of both the yield points. So yield strain, now what is the meaning of yield strain? That you can draw a line parallel to the initial linear portion. Here we can have drawn that particular line to the initial portion, and that particular intersecting curve is the yield point, and y coordinator of this particular point is the yield strain. So that y coordinator is here. This will be sigma y, that is the yield strain. Now ultimate tensile strain means what? The maximum ordinate in the stress strain diagram is the ultimate strain or the tensile strain. This is the maximum load the specimen sustained during the test. So it is just a highest load where the particular component will not be failed, but after that the neck formation has been started. So what is the meaning of necking? This is the phenomena that after the ultimate tensile stress, the cross sectional area being to be decreased in the region of the specimen because of local instability. So whatever the crystal structure that has been disturbed, and then the neck formation has been started, and after necking has been beginning, we note that rupture occurs at an angle of 45 degree with the original surface of the specimen. So generally that rupture may be occurred. So rupture or fracture, that is nothing but the specimen split into the two or more pieces. So the rupture strength is the strength of the material at a rupture. This is also known as the breaking strength. So breaking strength means when at that point of rupture how much will be the stress. Based on that we are calculating that. So the plastic deformation, already this portion we have seen what is the meaning of plastic deformation. So basically here we cannot be able to or unrecoverable strain, that is nothing but the plastic deformation. So the most material in the linear elastic category are usually capable of the plastic deformation. Brittle material like ceramics do not experience any plastic deformation and will fracture under the relatively low stress. So there will not be any kind of plastic deformation in the brittle materials. Directly that material will be gets failed. So this will be the behavior for the low carbon steel and the aluminum alloy, how the rupture has been occurred. So here will be the yield point for the aluminum, directly that will be goes, and here that yield point, upper and lower yield point we are getting in case of low carbon steel. So these are the terms related to the percentage elongation. A standard measure of ductility of a material is the percentage elongation, which is defined as, this is the formula. So LO is the initial length, LB is the final length divided by original length into 100. So we are getting that percentage of elongation. So for the commonly steel, the standard elongation is 21 to 30%. Now how the percentage of the reduction area has been calculated? So it will be a naught minus AB divided by A naught. A naught is the initial area, AB is the final area of rupture. So when that exactly failure will be occurred, we have to calculate that area again, and this will be again divided by the A naught, that is the initial area. So generally the percentage reduction in the area for structural steel, it is 60 to 70%. So for the ductile material, having the percentage of elongation above 5, for the brittle material, the percentage of elongation will be below 5. So these are the general terms related to the stress strain diagram for the ductile material. Now the stress strain diagram for the brittle material, so brittle materials such as cast iron, glass, concrete or carbon fiber. So these are the brittle materials. Now for the example is that if we want to pull the glass, we cannot be able to pull it. Means directly that glass will be gets broken into the number of pieces. The glass will not be elongated as much. So this will be the phenomena of brittleness, and they do not have any kind of that yield point in case of that when the material is the brittle. So here we can be able to see the stress strain diagram. Basically that elastic region it is there, so somewhat portion it has been extended, and suddenly that will be reached to the ultimate strength and the fracture will be occurred. So directly it will breaks into the pieces. So this will be the ideal stress strain diagram for the brittle material. So this will be the stress strain diagram. Might be for cast iron also you are getting this kind of the diagram. Only the stress will be goes on increasing and directly the fracture will be occurred. So any necking of the specimen in the case of the brittle will not be noted. Okay, so neck formation will not be there directly, that in that as it is portion or area this particular failure is occurred. So this is the stress strain diagram for cast iron generally, so which we have seen in the previous. So this is the in the practical event that experiment has been performed, this will be the practical diagram for cast iron. So how much is the stress that is in the MPa 375 will be the, or might be up to the 400 it has been reached, and this will be the strain values for the cast iron. So I think now you have cleared about the stress strain diagram for the brittle material as well as for the ductile material. So in the next lecture we will see the engineering stress strain diagram and true stress strain diagram. So thank you very much for the patience listening.